Hi and welcome to Unit 2, Topic 2, Video 13. In this video we're going to explore simplifying trig functions in the form a cos theta plus b sin theta. And the big picture here really is that if we have an a cos theta plus b sin theta, unless that's equal to 0, then it's quite hard to solve an equation involving those, and it's quite hard to visualize the function and to do really a lot with it. So if we can simplify that down to one trig ratio, then we're in a good place. And I'm going to show you that that's possible. So the learning goal, success criteria as usual, and here's our information. So y equals a cos x plus b sin x, or theta, it's all more complex variations. They're pretty common in a range of contexts, so adding them together is actually a really common thing to do. Music, sound waves, for example. Unfortunately, this form is a very difficult form to solve for x and to understand the graph, as I just said. So consider the graph of y equals 4 cos x plus 3 sin x. You'll notice that you know a lot about 4 cos x, you know a lot about 3 sin x. So 4 cos x has an amplitude of 4, 3 sin x has an amplitude of 3. So if you add 4 and 3 together, you might suspect an amplitude of 7, but actually, so it's not on, oh there we go, it's there, it's got an amplitude of 5. And that of course is because the cos x and sin x are apart from each other because they have a different phase shift. Sine starting at a midline and cos starting at a peak. So that 4 and 3 amplitude never really meet and add together to make 7. In fact, the peak occurs at 5 and it occurs here, which when I just zoom in on this scale, what is that? A little bit more than pi on 4. So there's a nice value for that, but that value is not clear and obvious. We also get this nice x-intercept of negative 0.644, which doesn't really sit well in any variational form of pi. So it creates this bit of an odd function that we've got to deal with. But we do notice that this function looks like a single periodic function. So we should be able to write this down as y equals something, let's call it a sine, and then we have x minus, and we use alpha, or y equals a cos x minus alpha. Now we'll change some of the notation a little bit later on, but it can be written as a single trig function where it's just some sort of phase shift on cos or sine to make that work, and we know that a is 5. So what about if we were dealing with sine cx, sine dx, or cos cx, sine dx? You can have a play around with that with Desmos if you want. You'll notice some patterns start to occur that are really important, and I'm going to show you what those patterns are now. So here's a generalization. We actually start by working backwards. So I'm going to start by where we're heading. Just because I know that's where we're heading, we don't have to redo this maths again because somebody's done it before us. So I know from previous work in this topic that the expansion of r cos x minus alpha is equal to r times cos x cos alpha plus sin x so on alpha. That's one of our, this is actually the sum difference, or the angle difference formula, and it's on the formula sheet. So if we define r as the hypotenuse of a right angle triangle, which I've drawn there, so I'll just throw the right angle in here, with lengths a and b, I've just made those up, so they're not special to the question yet, but we have lengths in a and b, then we know that r is equal to the square root of a squared plus b squared. Now we've seen this before. This is our work on moduluses, in vectors, in complex numbers, it's the argument, so we've seen this kind of stuff before. But what it means is that in this right angle triangle, cos alpha is equal to a over r, and sin alpha is equal to b over r. And these will be important for later on, so remember those. And that means that in our expansion above, you'll see I've done that blue dotted line down to where the equal sign continues, cos alpha becomes a over r, as stated here, and sin alpha here has become b over r. And so we've got that expansion, which doesn't look like it helps as much, except when we realise that the r's cancel out. So we can divide the r out the front by the common r divider on the inside, leaving us with a cos x plus b sin x. And of course this looks suspiciously like what we were dealing with at the start. How do we write a function or an equation that has a cos and a sine component and combine it into a single sine component? Now you'll notice here, or a single cos component, I apologise. You'll notice here that we have x and x. We do have to have these same values on the inside of the functions at the moment. And of course, a and b can vary. So we could have 3 cos x and 7 sin x, for example. Now, we did sort of suggest earlier that you could play with this, which is what I'd normally do in class, and define where this can happen, where it can't. And it'll be obvious. So if you start plotting things with a sine cx, b sine dx, or a cos cx, etc., you'll see the ones that look like periodic functions and the ones that don't. And they don't always look like periodic functions. Here's my summary in orange, though. A cos x plus b sine x can be written as r cos x minus alpha, where r is equal to the square root of a squared plus b squared, and alpha is equal to tan inverse of b over a. Unless a question specifically asks you to identify it in terms of sign, this is going to serve the purpose that you need it to serve in pretty much all cases, because you can do a lot more with that function. But of course, if you do need to do it in terms of sign, we get this: a cos x plus b sine x is equal to r sine x plus beta, where r is equal to the square root of a squared plus b squared, and beta is equal to tan inverse of a over b. You can go through and do the maths if you'd like. Now I'm just going to float back up the top and show you this original function we had here. 4 cos x plus 3 sin x. So of course the r is 4 squared plus 3 squared, which is 25, and the square root of that gives us this 5. But the minus alpha bit is the interesting one. So this is our alpha, and it comes from tan inverse of 3 over 4, whatever that value is. Interestingly, I've actually labelled the x-intercept, which means that this is where our sine goes. So we get sine of x plus beta, and our beta is this value, 0.644. And of course, if we add a value inside, this is in radians, inside our sine function, it's going to push it to the left, as we know. So it's got that shift, that phase shift to the left, which is what we're seeing here. So I reckon that if you do a little bit of tan inverse of a over b, 4 over 3, you're going to get 0.644 approximately. So there's our result and the concept. All the best.